Hello, friends. Welcome back to You Can Do TV. A turbine blade smaller than your forearm costs more than a decent car. 20,000 parts, 6,000 components in one turbine alone. 80% of the world's engines share one hidden supplier. And an engine never truly leaves the factory that built it, because what happens next may change how you see flying forever. You see the engine hanging under the wing and assume that's where the story begins. Every visible part exists because countless smaller improvements survived years of engineering trade-offs. Behind every modern turbofan are 3 decades of advances in materials, pressure ratios, and composite fan blades that shave hundreds of pounds off engines the size of a small living room. The Goliath sitting on that test stand is the payoff of billions spent solving problems most passengers never learn exist. What you're looking at isn't a factory, it's a convergence point. The core of a modern turbofan pulls together compressor stages, a combustor, and a high-pressure turbine. And every one of those pieces arrived from a different building, sometimes a different continent, sometimes a different continent. Engineers spend weeks aligning fan stages, threading sensor cables around casings, dropping the rotor onto an electronic balancing machine to hunt for wobble measured in fractions of a millimeter. The first core run on a new engine spins up to 7,000 RPM inside a locked test cell. After that, it gets sent somewhere far more unpleasant. "20,000 components. One engine. That is the number sitting behind the shiny cowline you glance at while boarding, and it's the reason a single assembly hall for the most efficient aero engine in the world looks less like a production line and more like a slow, deliberate performance by cranes and lifting rigs. Fancies arrives from a shipping container, wrapped like a museum piece. Gearboxes and drive systems bolt onto its perimeter. Fuel lines, hydraulic lines, and cable harnesses get routed with the patience of someone who knows a single misplaced clamp can ground the whole aircraft. Intermediate pressure compressor modules drop in from above. Engineers measure, torque, and lock wire every fastener by hand. Because in aviation, close enough is how you end up on the evening news. Then the entire core gets tipped horizontally on a specialized cradle. The central shaft slides through the compressor stages, and the fan module joins from the front, cranes doing the heavy lifting, human hands doing everything that actually matters. Fan blades go on last, each one balanced against the others so precisely that the finished rotor could sit on a coin without leaning. The nacelle cladding wraps around like a tailored suit. Then the whole thing gets moved on overhead rails into a test chamber and lit up for the first time. When it passes, technicians cap both ends in bright red covers, drape it, and hoist it onto a truck. Every one of those 20,000 parts has already been sourced, forged, cast, machined, coated, inspected, and delivered from somewhere else. Assembly is just where the bill comes due. The first bill was written in the foundry. Metal has a temperature ceiling, and modern engines blew past it years ago. Inside the hot section of a turbofan, air gets compressed, ignited, and rammed through the turbine at conditions that would turn ordinary superalloys into slag. So engineers stopped trying to make metal survive. They built something else entirely. Ceramic matrix composites are silicon carbide fibers, thinner than a human hair by a factor of 5, embedded in a silicon carbide matrix and wrapped in a proprietary coating, tough like metal, not brittle like your grandmother's teacup. The result is a material 1/3 the density of the nickel alloys it replaces, and capable of surviving temperatures roughly 500 degrees Fahrenheit, hotter than the best superalloys available. Why does that matter? Cooling air. Every turbine blade in a hot section normally has to be shielded by pressurized bleed air just to survive. CMCs need dramatically less of it. That freed cooling air gets rerouted back into the main flow path, improving thrust by up to 25% and cutting fuel burn by roughly 10%, which is the sort of number airlines will physically hug you for. The bottleneck was never running the material hotter. It was making enough of it. Pilot facilities now produce CMC turbine shrouds by the tens of thousands per year, scaled up from a handful of certification parts. Mass production finally caught up with the physics. A turbine blade is smaller than your forearm and costs more than a decent car. Understand how it's made, and the price stops looking absurd. The blade begins as a digital model shaped around thermal aerodynamic and mechanical constraints simultaneously, no small feat. That file feeds a method office, which designs the tooling to produce it, industrially using a technique roughly 6,000 years old, lost wax casting. A ceramic binder gets engineering secrets. A ceramic binder gets injected into machines to form the internal cores that shape the blade's hollow cooling passages. Those cores get baked in sand to harden without deforming, then placed inside injection molds. Wax gets shot in around them, forming clusters of wax blades that are inspected by ultrasound and X-ray to confirm the core sat perfectly centered. A crack invisible to the eye now becomes a crack invisible in flight, which is considerably less charming. The cluster gets dipped repeatedly in ceramic slurry until a thick shell forms, then autoclaved under pressure to melt the wax without cracking the ceramic. Molten superalloy pours in, directed solidification, controlled cooling through a ring, grows the metal grains along a single axis, giving the finished blade its thermomechanical performance. The cost stops looking absurd. It starts looking cheap. Everything upstream of the turbine blade begins with nickel-based superalloys engineered at the atomic level. Polycrystalline, directionally solidified, and single crystal versions each solve heat differently. Ceramic coatings, internal cooling passages, and microscopic film cooling holes let blades survive temperatures 100 to 150 degrees hotter. The material lives. Now it has to be shaped. And the shaping is arguably harder than the making. A 5-axis mill doesn't cut metal. It sculpts the path air will take through the engine. Every curved surface, every thin trailing edge, every twist along the airfoil exists to steer high-energy flow into the next stage without losing energy. Deviate by micrometers and you get vibration, hot spots, or a compressor stage that quietly bleeds efficiency until nobody can find the cause. In this world, a shiny piece of metal is worthless. A shape is priceless. A blisk is blade and disc grown together as one piece of metal, which sounds simple until you try to make one. A cylindrical billet gets locked onto the table. The head begins hogging out material. The billet tilts, rotates, and swings as the tool descends into gaps between what will become blades. Carving from the outside in, one axis chasing another to reach angles a 3-axis machine could never touch. Rough passes leave witness marks. Finishing passes erase them. Then the shape emerges. On one titanium blisk, engineers cut milling time from 200 hours to 35. That is an 83% reduction achieved by combining mill-turn strategies with conical barrel cutters, saving roughly 18,150 pounds per blade, and slashing tooling costs by 72%. Numbers like that decide which supplier keeps the contract. After machining, the surface still isn't done. Robotic arms carrying belt grinders and spindle tools thread into the tight gaps between blades. Guided by laser calibration and probing, coolant sprays constantly to prevent overheating. Target surface roughness sits between raw 0.4 and 0.8 micrometers. A rough blade is a slow blade. The real challenge with blisks isn't cutting metal, it's writing the tool paths. Dedicated multi-axis roughing and finishing strategies now generate paths in a fraction of the old time, hitting tolerance and deadline together instead of choosing between them. Watch a 5-axis machining center work on a blisk for 10 minutes and you stop thinking of it as a machine. The table swings, the head rotates in sync. Coolant hits from both sides in synchronized jets, flushing chips out before they can score the finish. Roughing carves the walls between what will become blades, one deep pass at a time. Then finishing takes over, running along the root fillet where blade meets hub, the trickiest surface on the entire part and the one that decides whether it holds up under load. Now the shape exists, but one shape isn't an engine. Thousands of them are. Thousands of finished parts. Hundreds of finished parts, hundreds of factories, one assembly line where every prior mistake either disappears or gets exposed. A 50-50 joint venture between two continents built a family of engines with more than 31,000 units delivered on the predecessor alone and over 14,000 orders on the follow-on. That scale doesn't happen by accident. The first engine off any new line gets shipped in the dead of night. It rolls into a test facility, gets hoisted onto a rig, connects to sensor arrays and fuel lines, and fires up. 2 days ahead of schedule in this case. Aerospace almost never runs early. Note the date. The variant for the single-aisle jet family reached its first engine run. Engineers walked the test cell, torqued the last fittings by hand, cross-checked laptop readouts against the physical hardware, and confirmed sensor cabling wrapped tight against the casing. Then the throttle came up, the fan spun. everything held. The core module gets built on one continent, the fan module on another, final assembly in a third country. Then a truck delivers the whole thing to the aircraft plant. 2 production engines rolled out the door 2 days ahead of schedule. A whole ship set, ready to fly. A pulse line is what happens when someone finally admits that assembly workers are humans, not machines. Instead of one giant station where a fitter climbs, stoops and hunts for tools, the work moves through discrete posts with adjustable height fixtures, constant overhead lighting, ergonomic lifting aids, and part carts pre-staged by logisticians. Every fastener, seal, and gasket sits exactly where the fitter's hand will reach next. The target is 48 accessory gearboxes leaving the factory each week, the kind of throughput that only comes from removing every wasted second between operations, which sounds obvious. It wasn't for decades. One manufacturer covers a thrust range from 9,500 pounds to 115,000 pounds, the difference between a business jet and a wide-body's entire wing loading. That span demands metal 3D printing, woven composites, and 2,500 engineers doing nothing but propulsion R&D. Now the engine is built. Getting it certified is the next problem. A test cell is not where an engine is celebrated, it's where engineers try, deliberately, to break it. A program that historically ran 22 months from design to first firing was compressed to 15 months minus 3 days, not to rush certification, but to buy more time inside the cell, hunting failure modes before the sky finds them first. The largest low-pressure turbine ever built, 10% bigger in diameter than its predecessor, uses titanium aluminide blades grown by additive manufacturing at half the density of standard nickel alloys. Airfoils get tested against moving bars, simulating unsteady effects, then on rotating rigs, then in the full engine. Now it's allowed to fly. Some engine problems never require removing the engine from the wing. Field service teams can reach aircraft worldwide within 24 hours, bringing specialized tools and replacement parts directly to the airport. The goal is rapid response, not necessarily an immediate repair. Thousands of maintenance tasks are completed each year, including engine changes, service bulletin updates, bore scope inspections, and blade blending through inspection ports without dismantling the engine. These procedures restore aircraft to service much faster than major overhauls. Every hour an airliner remains grounded disrupts schedules, delays passengers, and increases operating costs, making fast maintenance almost as important as the engine itself. Some aircraft maintenance, repair, and overhaul work is fast, precise, and looks deceptively simple. Installing a rear spinner cone on a widely used single-aisle engine takes patience most people don't associate with jet engines. Guide pins go in first. Three of them equally spaced, with one at the offset hole that lines up with the number 1 blade position marked by a small sphere. A heat gun warms the rear cone flange to a specific temperature, verified by a thermocouple. 12 lubricated bolts get torqued in a crisscross pattern. 6 clearance checks with feeler gauges confirm the gap. Miss any step, and the fan won't forgive you. Not every repair happens on the fan. Installing the variable frequency starter generator sounds routine until you damage a carbon seal and add days to the job. A spline alignment tool pre-aligns the generator shaft to the accessory gearbox using a bubble level. Small tool, huge time saver. When on-wing fixes run out, the engine comes off and comes home. More than 300 engines from customers worldwide pass through this Petropolis facility every year, each arriving after 1,500 to 15,000 flight cycles. Disassembly, cleaning, inspection across more than 12,000 components, repair, reassembly, and full test cell validation, all done in about 65 days. Zoom in on one component inside that overhaul flow, and things get weird fast. A used combustor arrives in a wooden crate looking like something you'd throw away. Then it gets rebuilt to like new condition. Watching the process is genuinely strange, because half of it looks industrial and half of it looks like a spa day for jet parts. Technicians crack the crate, lift the combustor onto a rotating stand, and separate its layers using rubber mallets. Yes, rubber mallets. On a jet engine part. Aerospace is weirder than the brochures admit. Masking tape gets applied to protect the areas that shouldn't be touched. A robotic arm sprays thermal barrier coating across the surfaces that face the flame front, restoring the heat shield the original ceramic coating gave up over thousands of cycles. The combustor goes onto a large CNC lathe. Cutters remove damaged material and true up the flanges. Robotic laser welding rebuilds structural seams with precision no human hand could match. Ultrasonic cleaning tanks, fluorescent penetrant baths, and coordinate measuring arms verify every dimension before the whole assembly gets packed, sealed, and shipped back looking bright, straight, and ready for another life. Now widen the aperture. Overhaul is not a commercial airline story alone. It stretches across military, naval, and rotorcraft fleets running the same discipline. Inside a full maintenance, repair, and overhaul facility, turbine rotor blades come off the shaft and get mounted onto circular fixtures for inspection. A Keiko UK robot arm carries them through non-destructive testing. Fluorescent penetrant, magnetic particle, eddy current, ultrasound, radiography, thermal imaging. Each method looks for a different kind of crack, a different depth of damage, because probably fine is not an aerospace phrase. Engines from military helicopters, single-seat trainers, and the low-bypass turbofans on multi-role fighters all pass through the same style of overhaul. Some go through complete afterburner refurbishment. Others go into acoustic test cells for bench setting and final resolution testing. Marine gas turbines on warships get the same discipline applied to the same tolerances, in the same tanks, by the same trained hands. The engine landed. Its shift never ended. Its shift never ended. But maintenance, repair, and overhaul don't just fix. It forces redesign upstream. The biggest obstacle was heat. Higher pressures and temperatures wore turbine blades faster than the original design promised. A redesigned blade with 40% more coolant flow solved it, and double time on wing. No single engine factory makes everything itself. More than 6,000 components of the largest low-pressure turbine ever built, over 80 inches in diameter, arrived from Japan, the US, Italy, France, and Poland before final assembly. Some of those 6,000 pieces cannot be milled. They can only be grown. Direct metal laser sintering and electron beam melting print blades from ultralight titanium aluminide layer by layer. The inside geometry of a modern blade matters as much as the outside, and traditional machining simply cannot reach it. Not every hidden supplier makes exotic parts. Some just make gearboxes. Some just make gearboxes, and nothing on the aircraft moves without one. More than 50 years of accumulated experience sits behind the accessory drivetrains and power gearboxes co-designed with engine makers, quiet supplier work that decides whether hydraulic pumps, fuel pumps, and generators actually get the torque they need. Aluminum and magnesium castings arrive from a dedicated gravity and low turbulence foundry, feeding more than 4,800 gearbox housings per year. Machining happens in another facility entirely, producing over 40,000 gears annually inside lean production cells dedicated separately to turbofan, turboprop, and helicopter transmissions. Different aircraft, different loads, different noise limits. One factory floor cannot handle all three properly, so it doesn't try. Final assembly and testing verify each unit before it ships to whichever engine plant needs it next. Over 600 million service flight hours already logged on this class of hardware. That number does not happen without the boring parts. The next supplier tier is already testing hydrogen fuel cells inside megawatt-class hybrid propulsion, an advanced turboprop core paired with an electric motor, the parallel hybrid architecture aiming well beyond 2020 state-of-the-art regional aircraft performance. Ask most people what makes a plane fly, and they'll point straight at the engine. But an engine alone doesn't create flight. Behind it sits an entire network of wires, welds, electrical spines, fuel systems, and test benches most passengers never notice. An aircraft needs thrust, but it also needs a nervous system. You're looking at 50,000 harnesses a year, each built to survive temperatures from 55 degrees Celsius to plus 250 degrees Celsius. Over 20,000 go into landing gear alone. That range reflects real conditions between cruise altitude and a hot runway in Dubai. Production begins in a design office, where specifications become 3D harness models. 5-axis machines cut fittings, chemical baths, prepare surfaces, tubes are bent precisely, and protective coatings insulate every internal path. Cables get routed on a jig, cut to length, stripped and terminated by crimping. Every finished harness gets tested for resistance, insulation, and high voltage. Every single one, no sampling. Then it ships to an assembly line to become part of an aircraft that would not fly without it. Horses are one strand of a much larger electrical spine, one that keeps growing every generation. Power generation supplies the energy. Distribution units manage and protect the network. Wiring transmits both power and data. Conversion solutions step voltages up or down for every subsystem. Ventilation systems handle air quality, cabin comfort, and safety. Now electric motors are entering propulsion itself. Fully electric small aircraft already fly using this hardware. The next single-aisle generation will run more electric systems and hybrid architectures, meaning the invisible layer keeps growing while the engine barely changes size. Underneath every electrical run and every fluid line sits a physical joint, and welding is not a background trade in aerospace. A weld on engine tubing sits at roughly 800 degrees Celsius during work and must resist tension, pressure, vibration, and heat cycles forever. Beautiful means nothing. Certified, testable, and load-bearing is the entire job. Even the fuel and the test bench behind the engine belong in this invisible layer. Production engine test benches are now running biofuel blends from waste oils and animal fats, targeting 35% by 2025 and avoiding nearly 10,000 tons of CO2 emissions annually. The test cell had to be modified too. Nothing about this is casual. Nothing about this is casual. Behind every engine sits enormous machinery. Behind the machinery sits people, and increasingly, robots that work with them, not instead of them. A cobot polishes titanium, leading edges only after an operator teaches it to motion first. Numbers help. One engine assembly site alone employs 2,500 people, has delivered more than 8,500 engines over 3 decades, and is now hiring 100 more just to restart large engine work. That is one site at one company in one country. Multiply across the industry, and the invisible workforce becomes staggering. Passengers see a logo. Accounting sees everything else. Zoom out from one site to the culture behind it. Engineers from more than 50 countries share workshops across multiple sites just to develop propulsion. 7 engine families in 30 years. Full system capability at one location. The machine works because the culture does. Then follow those engineers out of the factory and into the field. Over 500 million flight hours logged. Behind that number are more than 500 field operators running 24/7 support and health monitoring. The humans reading data the sensors alone cannot interpret. Large modern engine will pull 3,600 pounds of air every second at takeoff. That would evacuate Madison Square Garden in seconds. The world record for thrust, 127,900 pounds, belongs to this family. That record was set by blades built essentially by hand. Now scale that to over 30,000 blades produced to date at 65 units per week. Each blade is built from more than 1,700 pieces of carbon fiber shapes, each about the thickness of a playing card laid up individually by hand. After layup, the blade gets cured, precision machined, and dimensionally verified. Then it moves through CT scanning, X-ray, and ultrasonic inspection to catch anything invisible from the outside. A single hidden void in the wrong spot could bring down an aircraft, so nobody blinks at the inspection bill. Titanium edges get bonded on. The finished blade gets painted and passes through another round of quality checks before shipping. Total build time per blade, about 340 hours. One inspected blade recently returned to service after roughly 28 million miles, the equivalent of 117 trips to the moon. After minimal refurbishment, it went back on the wing. That is not marketing. That is durability that keeps entire fleets economical. Every field failure feeds back into the next design. Advances in computational fluid dynamics and manufacturing let engineers place cooling exactly where hotspots proved they were needed. The physical evidence dictated the redesign. A better blade only matters if the maintenance, repair, and overhaul shop can install it fast, so the shop scales up too. A single aftermarket support facility was expanded specifically to install a new high-pressure turbine blade that doubles time on wing. Blade stockpiles were built up before certification finished, just to be ready. New MRO capacity is coming online across Asia, Europe, and the Americas simultaneously, because a modification is only as fast as the shop that installs it. Now pull back and look at how deep the supplier network actually runs. Roughly 80% of the world's aircraft engines contain at least one component from a single Italian supplier network, and most people have never heard of it. That is what a modern supply chain actually looks like. The same network spans 4 continents, produces low-pressure turbine hardware for wide bodies, power gearboxes with over 40 years of accumulated design experience, MRO services across a global footprint, and marine transmissions on aircraft carriers. R&D happens in partnership with universities across multiple cities. Nobody at cruise altitude is thinking about any of this. That is the point. And zoom in on one participant to see how distributed the work has become. 11 plants and labs, 10 R&D clusters, over 1,500 suppliers. Sites specialized by discipline, heavy machining in one town, foundry work in another, additive manufacturing in a third dedicated to metal 3D printing, turbine cases in yet another country. You cannot fit this many capabilities under one roof, so nobody tries. The whole system runs distributed, and it works. Then there is the next tier down, a family firm founded in 1903 that most passengers will never hear about, but whose fuel systems, actuators, and landing gear equipment ship worldwide. 75% direct export to global aircraft manufacturers, 60% civil work, 40% military. That split alone tells you how strategic these small suppliers actually are. Environmental chambers running to minus 21 degrees Celsius, anechoic chambers, X-ray inspection, direct fire resistance testing. Each qualification test costs weeks and eats specialized hardware most industries have never seen. The same industrial model runs across every precision manufacturing sector that matters. Dozens of consolidated companies, 4 continents, both original equipment manufacturers and Tier 1 suppliers, served simultaneously. Decentralized autonomous plants respecting local decisions. Deep technology diversification so customers can pick whichever process fits their part best. This is how components for anything critical get made now. Aerospace is not an exception, it is the extreme version of the same playbook. Now go deeper still into the tier of suppliers that most engine factories cannot replicate in-house. Vacuum coating specialists run entire facilities dedicated to thin film deposition using ion beam sputtering, magnetron sputtering, electron beam evaporation, plasma-enhanced chemical vapor deposition, and diamond-like carbon coatings. A single ceramic thermal barrier on a hot section blade is exactly this kind of engineering, just tuned for combustion temperatures instead of light wavelengths. Inside these facilities, ion beam-assisted deposition systems, the size of small trucks, apply nanometer-precise layers onto substrates positioned in ultrasonic cleaning systems beforehand. Design departments run their own control software written in-house because commercial coating software doesn't handle the tolerances required. So they wrote their own, obviously. Every aerospace hot section component that survives 2,400-degree-plus environments does so because someone in a facility like this figured out the coating recipe first. You will never see their name on the engine. But without them, the engine burns. One industrial base, multiple extreme industries. The same robotic filament winding and composite construction that builds rocket motor cases also builds fan cases for jet engines. That's the point. One engine, hundreds of factories, thousands of engineers, and millions of inspections. That is what actually gets an aircraft into the air. From the cabin, the engine looks simple: a fan beneath the wing, rising thrust, then the push into the seat during takeoff. Behind that familiar moment are composite fan blades cured for 340 hours, turbine blades cast from single crystal superalloys, titanium blisks machined on 5-axis mills, ceramic matrix composites surviving extreme heat and maintenance, repair, and overhaul facilities working around the clock worldwide. The engine leaving the factory is only the beginning of its manufacturing journey. If you had to choose one breakthrough behind modern jet engines, would it be materials, manufacturing, or maintenance? Let us know what you think. Thanks for watching. Hope the breakdown was worth it. Subscribe if you want to keep following the supply chains most people never see. We'll be back soon. Take care.